Let's look at statement 5.84 together. The statement states, if A, B are subsets of X, then FA union B equals to FA union FB. So the goal of this proof is to prove set equality. In order to prove two sets are equal, we need to prove the forward containment, which is FA union B is a subset of FA union FB, and the backward containment, FA union FB, is a subset of FA union B. First, let's prove the forward direction. As our first step, let's let X in FA union B. What does it mean by X is in FA union B? Let's draw some pictures. Here we have our domain X and codomain Y, and function f takes elements in domain X to codomain Y. We know A union B is a subset of X, and if we apply f to every element in A union B, then we will get a new set in codomain, which is FA union B. That being said, if X is in FA union B, then X equals to Fy for some Y in A union B. Let's write those in words. If X is in FA union B, then X equals to Fy for some Y in A union B. Since Y is in A union B, then Y is either in A or in B. If Y is in A, then X equals to Fy, which is in FA. If Y is in B, then X equals to Fy, which is in FB. So we know X is in FA or X is in FB. By using set notation, we have X is in FA union FB. So at the beginning of the proof, we let X be in FA union B, and now we have X is in FA union FB. Thus, we can conclude that FA union B is a subset of FA union FB. So now we have proved the forward direction. Let's prove the backward direction. First, we let X in FA union FB. Then we know X is either in FA or in FB. If X is in FA, by the same analysis we did for the forward direction, we know X equals to Fj for some J in A, and observe that J in A and A is a subset of A union B. So J is in A union B, and so Fj is in FA union B. Thus, X equals to Fj, which Fj is in FA union B, so X is in FA union B. Similarly, if X is in FB, we know that X equals to Fk for some K in B. Since K is in B and B is a subset of A union B, so we know that K is in A union B. Thus, X equals to Fk, which Fk is in FA union B, so X is in FA union B. No matter if X is in FA or X is in FB, we get X is in FA union B. At the beginning of the backward direction, we let X be in FA union FB, and now we have proved that X is in FA union B. So we can conclude that FA union FB is a subset of FA union B. Now we have proved both directions. So we say that the set equality holds. So FA union B equals to FA union FB. Let's take a look at the next statement. Statement 5.85. It states, if A and B are subsets of X, then f of A intersect with B equals to the intersection of FA and FB. To better understand this statement, let's look at a concrete example. Let's draw a xy plane and set the domain and codomain both to be all real numbers. So here, x-axis represents the domain, and y-axis represents the codomain. Consider function f(x) equals to x, with a be the closed interval from 12 to 25, and b be the closed interval from 20 to 30. We want to see if the intersection of fa and fb equals to fa intersect with b. First, we graph our function on the xy plane. Then let's try to find fa. So we apply f to every element in A, and we get a new set in our codomain, which is fa. And then we apply f to every element in B to find fb. The intersection of fa and fb is just the overlap between fa and fb, which is the closed interval from 20 to 25. Now we know the intersection between fa and fb. Let's figure out what is fa intersect with b. First, we observe that the intersection of a and b is just the closed interval 20 to 25. Then we apply f to every element in the set. We get fa intersect with b, which is simply the closed interval from 20 to 25. In this example, the statement holds, but I encourage you to apply similar analysis on other functions to see if the statement still holds. We've tried a linear function in this example. I will leave you a small hint. Maybe try some quadratic functions, like x squared or some of that kind. One thing to note in the quadratic case, say if you want to know f of the interval 8 to 20, it's not just plug in endpoints into the function to get the image, like what we did for the previous example. We have to apply f to every point on this interval, which we get these points. So the image should be the interval indicated on y-axis. The last thing I want to discuss about today is statement 5.91. The statement states, if C, D are subsets of Y, then the preimage of C minus D equals to the preimage of C minus the preimage of D. To prove this statement, we need to prove both forward and backward containment. That simply is, the preimage of C minus D is a subset of the preimage of C minus the preimage of D, and the preimage of C minus the preimage of D is a subset of the preimage of C minus D. Let's look at the forward direction. As always, our first step is to let x in the preimage of C minus D. Let's draw some pictures to better interpret what does it mean by x is in the preimage of C minus D. Here we have our domain x and codomain y, and function f takes elements in domain x to codomain y. We know by assumption that C minus D is a subset of y. The preimage of C minus D is a set of all elements of the domain that are mapped into C minus D in our codomain. That simply means every element in the preimage of C minus D gets mapped to C minus D, and every element outside the preimage of C minus D gets mapped outside of C minus D. So, if x is in the preimage of C minus D, then fx must be in the set C minus D. So let's write that in our proof. If x is in the preimage of C minus D, then f of x is in C minus D. I think this will help you get started with this proof.